Here we have section 3.4, and we're defining a basis. And it's pretty straightforward. Okay, so our definition, and they call it definition 3.4.1, is that vectors x1, x2, up to some xm belonging to they use subspace. I mean, you know, it could be space, but anyway, subspace S are said to form a basis, okay, if they meet two conditions. So I guess I'll go with A. Now the way they say it is every vector in S, is a linear combination of x1 up to xm. Now, we can say it a little simpler, and that is that instead I could say x1 up to xm span S. Okay, because that's exactly what span means. It means every vector in S is a linear combination of those vectors. So we could just say it spans S, and that's typically the way I would say it. And then B, they are linearly independent set of vectors. So x1 to xm are linearly independent. Okay, so there you go. That's all it takes. And so if you're checking to see if something is a basis, those are the two things you would check. Does it span, and are they linearly independent? So an example, now I don't think they have used this term yet, but an example would be, for instance, the set of vectors E1, E2, and then En. You know, I'm not sure why they start with M up here in the definition and then go to En, but I would have used N up in the definition. But at any rate, these vectors, so and remember what they would be if I name them like this, you know, up to an En. I assume that what I have is, you know, E1 is the vector 1, 0, 0, 0, 0. Down here, enough zeros that it's an element of, say, Rn. And then E2, 0, 1, 0, 0, 0, you know, all the way down. And so forth all the way to En. And that would be 0, 0, 0, dot, 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 all the way down to 1. And these are all, you know, n-dimensional vectors. So this set of vectors is a basis for Rn. Okay, and pretty simply, I can see first that it spans. right? Because if, something like A1, A2, all the way down to AN, that's an element of Rn, but I can write that as A1 down to AN is equal to A1 times E1 plus A2 times E2 all the way to En, so AN times En. And so there we've got the span, right? So spans. So the EI span Rn. And then, well, it's pretty obvious they're linearly independent since if we take the matrix, E1, E2, all the way to En, this is equal to the identity, N by N identity, and therefore we know that those are linearly independent columns. Okay, and what I would, get that right, I made a non-singular matrix, so the columns are independent. Okay, so there we have independence, so the EI are linearly independent. And we call this actually, this is the standard basis. Okay, so when we take these columns of the identity as our basis, we call that the standard basis. So now, but another example that's not standard would be, something like this set here, 0, 1, whoops, well, sure, that'll work, and 1, 1. I was going to write 1, 0, but that'll work. Okay, we take that is our S, and in that case, these vectors do span all of S, and they're linearly independent. Now, it's obvious they span. Okay, so span is obvious in this case because I made S from the span of my two vectors, 0, 1 and 1, 1. Okay, that's what this means up here, is I made them from the span. And so the span part's obvious. Now, are they linearly independent? And sure, they're linearly independent. If I set up this matrix 0, 1, 1, 1, I can flip the rows and make that 1, 1, 0, 1. And then subtract row 2 from row 1, put it back in row 1, and I get to the identity. So it's a non-singular matrix, and so we have independence there. Okay, so there are a couple of examples and our definition. Let me do another example. So here's a non-matrix type example. Okay, so here's example. And the vectors 1, x, and x squared form a basis of polynomials of degree 2 or less. Okay, and again, this is actually the standard basis for second order polynomials, or P2, I guess I could call it. This is the standard basis. And, you know, okay, if, so we'll call this subspace of all functions and so forth, I guess, P2. And if I have an element of P2, so it would be something like ax squared plus bx plus c is an element of P2. Well, then we see that x squared, x, and 1 span this subspace P2 because I did it right there, right? I have that this polynomial is exactly ax squared, okay, plus bx plus c times 1. So there's my other vector. So here is a linear combination of my 3 vectors, x squared, x, and 1. And so we have spans P2. And then linearly independent, you know, can I write any of these, you know, x squared or 1 as a linear combination of the others? And no, I cannot, right? If I have ax squared plus bx plus c is equal to 0, that implies that a equals b equals c equals 0. So linearly independent. So you see this idea of vector spaces and basis and span and so forth is much, much bigger than vectors like this. Okay? We can think of vectors as being functions, and so we had these functions, the constant function 1, the x function, and the x squared function, and they form a basis for these second degree polynomials or less, and it is the standard basis. But I could come up with a different basis for polynomials of degree 2. You know, I could do something like, I think, probably x squared plus 1, maybe x plus 1, and then, oh, maybe like, I might even be able to get away with something like x squared plus x. I think that will do it. Now, I'm, you know, to show span, okay, well, again, you know, I have a given element. Can I write ax squared plus bx plus c as, now here I'm going to have to use different letters. I'll use Greek letters, as some alpha times x squared plus 1 plus a beta times x plus 1 plus a gamma times x squared plus x. And now I can set this up as a matrix sort of thing, right, by using like terms. If I go with the x squared, I have that, you know, alpha plus gamma has to equal A, and I have that where my x's, beta and gamma. Beta plus gamma has to equal B, and then finally, what's C? I need an alpha and a beta. Alpha plus beta has to equal C. So the question now is, can I find alpha, beta, and gamma to get this ABC? Well, that all comes down to writing this in a matrix form. I'll write it here, I guess. And if I have alpha for column 1, beta for column 2, gamma for column 3, you see I've got a 1, 0, 1, and an A. Then a 0, 1, 1, and a B, and a 1, 1, 0 for the C. Now, I really don't care what those are. The question is this over here non-singular? Because if that's non-singular, then I can always solve that no matter what A, B, and C are. And so there's the question. In order to get the span, is that non-singular? And then it also will answer the independence, because the question would be, well, can I get the zero quadratic from this? Well, if this matrix is non-singular, then the only way I could get all zeros on the right would be if I let alpha, beta, and gamma be 0. So I'm just, need to figure out, is that thing non-singular? And I believe, sure it is, right? If I subtract row 3 from row 1, so row 1, I'm only going to work with the matrix itself. So subtract row 3 from row 1 and put it in row 3. I'll get a -1 there and a 1 here. And then now I'm just going to add row 2 and row 3 and put that in row 3. So I get 1, 0, 1, 0, 1, 1, and 0, 0, 2. And then I'll have to divide by 2, and then sure, this will reduce, so R, E, F goes to the identity in 3 dimensions at this point. So yeah, this is non-singular. Okay, so this is non-singular. And so that means I can solve this situation here for any A, B, and C. And it has a unique solution because I can use the inverse and all that. And so that also means that if I use 0, 0, 0 to get the 0 function up here, then alpha, beta, and gamma had to be 0. Okay, so we get the span. Okay, so they span and linear independence. Okay, and so that means that those original vectors I was using here, there we go, that does form a basis for second-degree polynomials. Okay, so there is basis with some matrix examples and some non-matrix examples.